So now we will talk about a dry etching process. Dry etching process. For the dry etching, so this is the advantage for the dry etching. First, so we eliminate the handling of dangerous acid and solvent, and we use small amounts of the chemicals, and the etching can be anisotropic or vertical etch profile. For example, if we have the mask, if this is the mask, here is the mask. So for the white etching, the profile is like this. But for the dry etching, so the profile can be like this. So this is much better profile than the white etching. Then we have the faithful pattern transfer into the underlying layers, because the opening on the side, top and the opening on the bottom is the same. So this way we have the faithful pattern transfer. So we also get higher resolution and clean and better process control. So the disadvantage is some gases is quite toxic and corrosive. For example, we will use chlorine gas, so we know this is very corrosive. But there may be reseparation of non-volatile compound on wafers, and also the equipment is very expensive. So 200 to 500K for the research, a few $1 million for the industrial tools. But there are two types of the dry etching. One is the non-plasma based, so we use this for the gas phase. Another one is the plasma based etching. So first we look at the gas phase non-plasma based etching. For example, we can have this chemical reaction: a silicon plus chlorine gas to form the silicon tetrachloride. This one is volatile, but actually this will not happen. This will not happen at a low temperature because of the large activation energy. So we need very high activation energy for this reaction to take place. But when we have the plasma, there will be chlorine atoms. This will be a chlorine atom. So chlorine atoms, this will react easily with this chlorine atom will react easily with silicon to form silicon tetrachloride. So when we have the plasma, the reaction will take place very easy. So the one exception for the gas phase etching is the xenon difluoride. This one is actually very popular for the MEMS. So we don't have it at the University of Waterloo, but I know quite many clean rooms where they have this xenon difluoride for the etching of the silicon. So the etching is different. It's different from the plasma etchings. So some people think the xenon difluoride will convert to be xenon plus atomic fluorine. So actually, this is not the case. There is no atomic fluorine generated by the xenon difluoride. So the chemical reaction is different from the plasma etching use those kind of gases. And now let's look at the property of the xenon difluoride. So there is a white powder with the vapor pressure, good vapor pressure at room temperature. This isotropic etching with rough surface and has high selectivity over aluminum, silicon oxide, or silicon nitride. But we know that for HF, this one it will etch with aluminum, but this one, xenon difluoride, will not etch with aluminum or oxide or nitrate. The etching rate is fast enough, there is heat generated, and the xenon difluoride reacts with water or vapor to form HF. So we have to make it. We have to store it in a dry place. So why we need a gas phase etching when we can etch it for the wet etching? But this is because there is no capillary force. So if we do the wet etching, for instance, for the etching of silicon, so we can use mixture of the nitric acid and hydrofluoric acid to etch silicon. We can also use QH to etch the silicon. But when we have this wet etching, so we have the capillary force. But when we have the capillary force, this is not good for fabricating the freestanding structures. For example, if we want to make a structure like this, so we can start with the two layers. So here is the substrate. We have one layer here, and we have these two layers. But this silicon, this one can be another material. So we can do the lateral etching. To make something like this. This is the cantilever, for instance. Cantilever. So those cantilever structures is very important. Is very important for the MEMS, macro electromechanical systems. In that case, when we do the xenon difluoride etching, so this one will be good. If we do the wet etching, because of the capillary force, so this part will fall off, get collapsed, and become like this because of capillary force. But this is the main use of this gas phase etching of the silicon. Can we etch silicon oxide using a gas phase? No, not wet, no liquid. So actually, we can use vapor HF. So we can use vapor HF to etch with silicon oxide, and the purpose is the same to avoid capillary force. So now I can show you the example. So it is from this paper a comparison between wet etching and vapor. So this is vapor HF etching for the silicon oxide. So what do we want to make? So we want to make this kind of structures. So the bottom part is already etched away. So the bottom part is a silicon oxide is already etched away. So we get this kind of freestanding structures. To make this, we need to avoid capillary force happen in the wet etching. This is the vapor HF etching equipment. This is the HF vapor equipment. So you can see, so we bubble hydrogen. So we bubble hydrogen through this HF bottle. This HF bottle. So as a result, so we get the vapor of HF and the water. We also have the water vapor. So effectively, it is like a wet etching because we have water and we have HF, but they are both like a vapor phase. So we have very local chemical, like kind of very small scale wet etching, but so there will be no capillary force. So this is also very popular. The vapor HF is also very popular for the MEMS. So now let's look at the dry plasma etching. So there is the first plasma etching. We can have a directional etching because of the self barriers. We have the self barriers. So these self barriers is not applied externally. That means no DC power. We do not apply any DC voltage barriers. So actually, these self barriers come from it is created simultaneously in the RF plasma. So now we can look at, if you remember, we can look at again. This one is from the thin film deposition sputtering process, as you can see here. So when we have this is only RF, there is only RF power, no DC power, but we can have a very large voltage drop. So we can have very large voltage drop even with only RF power. No AC barriers. No DC voltage. So the RF is AC. Only RF power we can have large voltage drop. But this voltage drop will give the energy for the ion bombardment. Yeah, so this voltage drop, this is called the self barriers generated in the RF plasma. So this give you the directional etching. There are two components in the plasma. One is ionic species. This will result in directional etching. The other one is the chemical reactive species. This gives you very high selectivity and very high etching rate. Those free radicals and neutrals. This is the chemical species. For example, this is the chemical reaction for the casing of etching silicon. So where the chemicals come to the surface, reaction and pumped away. So now let's look at the plasma, taking CL4 as the example. CL4 plasma as an example. So there are first is the dissociation. So it becomes CF3 and F. So this one we know is very reactive. This is also very reactive. They are both free radicals, but this one is even more reactive than this one. So this is the ionization. So it creates some ions. Ionization. This one is the dissociative ionization, the combination of the two. So dissociation and ionization. This is excitation to the higher energy state. This is the recombination. So this is the reverse process from this recombination. So this one will generate light. This we call it glow. So this generates light, a glow. So this light can be used for the TV. So this is the glow, plasma TV. So plasma TV was popular about 10 years ago, but nowadays I think people only use mostly people use the LED TV. No longer plasma TV, only LED TV, TV. So now let's look at the loss mechanism in the plasma. So as seen in the plasma, we have unstable particles. They include ions, radicals, active atoms, and electrons. So they are generated. So the number will increase until their loss rate is equal to the generation rate, forming a steady state plasma. So now we look at how they are lost. What is the loss mechanism? How come they are lost? But this includes a recombination of ions and electrons, drift a diffusion to the walls and get lost to the walls, a recombination of the radicals, and also chemical reaction. So this is the dredging process. So this one is what we want for the dredging process. So in equilibrium, the degree of ionization typically is only 10 to the minus 3 or 10 to the minus 6 of the gas molecule. So only 10 to the minus 3 or 10 to the minus 6 of the gas molecule they ionized. But nowadays, so we have this thing, it's called HDP, high density plasma. High density plasma. So we will talk about the HDP later on in this lecture. For the high density plasma, so we can have about 10% of gas molecule get ionized, get dissociated to form the free radicals. So now let's look at the plasma etching mechanism. So in the plasma etching, so this is the overview. So in a plasma, so the reactive neutral chemicals, like the free radicals, but they are mainly responsible for the chemical reaction because they have much greater numbers compared to the ions. So those free radicals and the molecules also serve as the primary deposition species in the PCVD. For instance, so this one in the plasma environment will form something like this. So those things they are more reactive than saline. So why those free radicals are more abundant than ions? So because first they are generated at a lower threshold energy. Secondly, they are uncharged. Those free radicals, they are uncharged. They have longer lifetime in the plasma. So they come to the surface by diffusion because they are not uncharged. So they are diffusion. They are non-directional. So on the other hand, the ions are accelerated to the cathode because of the self barriers. So unless with very high energy, ion itself doesn't contribute significantly to the chemical reaction because it has the lower concentration. It's 10 times to 100 times lower concentration than the free radicals. But ion bombardment can help enhance the chemical reaction in ion enhanced etching. So first we look at the chemical etch, then we look at the physical etch. The chemical etch is highly selective and highly selective, high etching rate, but it is isotropic. So this is the example we have seen before. For the chemical reaction. So why they are isotropic? Why they are isotropic or nearly isotropic? So this is because of the arrival angle and the snaking coefficient. So first, so they are uncharged. So they have isotropic arrival angle. You can see they arrive different direction. They have different direction. They have the same chance. Then the secondly, the snaking coefficient is also very low. So we have talked about a snaking coefficient for the thin film. We have talked about the snaking coefficient concept in the thin film deposition chapter. For instance, evaporation is the S is equal to 1. So that's because if we have the substrate here, if we have gold and the comment here, and the snake here, this S equal to 1. For the spatter deposition, the S is less than 1 because it is more energetic. So if the ghost comes to the surface, it comes to this spot, and it will move around. Maybe snake here at the end. And this is smaller streaking coefficient. When we have smaller streaking coefficient, we get more conformal. More conformal deposition when it can move around. For the etching, so we have the same idea. But here the S is very, very small. For the case of for the fluorine, the streaking coefficient is only 1%. So that means, so when we have 100 fluorine coming onto the surface, only one has chemical reaction. So 99 will be boxed back. 99 of them will bounce back. That's why we can have the etching underneath the mask. This way we get undercut. This is called undercut. This is called undercut profile. For the oxygen, the fluorine, the streaking coefficient is only 1%. For the oxygen, the streaking coefficient may be higher, maybe 10%. It's much better. So again, this is the streaking coefficient. For the fluorine, the streaking coefficient is much less than 1, so it is isotropic. For the ion bombardment, this one S equals to 1. So because all the ions they come here, something will happen. But this here the reaction is the momentum transfer by the physical bombardment. So that means every bombardment will cause a momentum transfer. So that means we have the reaction, the physical reaction, right at the spot and hit the substrate. That's why we have S equal to 1. So we have the anisotropic. We have anisotropic profile. This bombardment gives anisotropic profile. So here's the example of etching of the silicate using SF6 gas. As you can see, it's isotropic. So we have the lots of lateral etching. It's almost the same as the white chemical etching, isotropic. So higher the power, higher the flow, higher the etching rate. So for the chemical etching, how do we know whether the etching will proceed or not? This depends on whether the product is volatile or not. We know for the white etching, we need the etching product to be soluble. We need the etching product to be soluble. For the dry etching, we need the etching product to be volatile. So whether it's volatile or not depends on the boiling temperature. For example, the silicon tetrafluoride, this is boiling temperature is minus 86 degrees boiling temperature. So this is very volatile. So this is good. But this one, silicon chloride, 57 degrees. This is not very high, but this is also good. For the copper, if we use the chlorine gas, then from the copper chloride. But here the boiling temperature is very high. So this one is not good, not volatile. The same thing, the fluorine is also not good. For titanium can be etched by the chlorine, so this is okay. So this is also okay. Not so good, but it is okay. So tungsten can also be etched. But copper, silver, nickel, gold, cobalt, platinum. So those metals, they cannot be etched by the palladium etching because the etching product is not volatile. So we have finished talking about the chemical etching. Now let's look at the physical etching. The physical etching is the ion bombardment. So we have the ions. We have those many ions in the plasma. They will bombard the surface. As a result, it is directional, non-selective, because the spatter used for different materials, they are similar. So 1 to 5. So that means the etching of the spattering of carbon is 1, spattering of gold may be 5. So the etching rate of gold is 5 times etching rate of the carbon. So we still say this is non-selective, not very high. 5 times is not very high. So it may result in a significant reseparation. So here is the spattering process. So we can have the pure physical etch. This is called the spatter etching system. Usually the self barrier is turned up to 200 volts. Ion energy is not very high for the efficient etching. Secondly, it has very low milling rate. So in the plasma, the milling rate is very low. It is only used for the cleaning only. If we clean if we etch away 1 nanometer, we said it's cleaning. So this is okay. But if we want to etch 10 nanometer, it will be difficult. It is difficult because first the energy is not very high. Secondly, so we have the gas molecule. So we have like a 10 milliliter. So we have 10 milliliter. We know so we have talked about a mean free path for the evaporation. So 10 milliliter give about 0.5 centimeter mean free path. You can imagine. So even though if this is gold, even though it's bombarded away, it will be kicked back because of the collision. So that means the material like a gold cannot be. So the material like gold cannot be thrown away from the target. It cannot go far away. It's hard to get far away. Far away because of the mean free path is only 0.5 centimeter. There will be a lot of collisions. Then it come out, then bounce back. Because of those two reasons, so the sputter etching is very, very slow. So to etch physically, we need ion millions. For the ion millions, so we have very high vacuum, and we have large mean free path because of high vacuum, and also high ion energy and higher milling rate. But we will talk about the ion milling later on. So we talk about physical etching and the chemical etching, but they both have the limit. So to get the good point from both mechanisms, this is called ion enhanced etching. In this case, it's also called chemical etch assisted by the physical bombardment. So we know that first, ion enhanced etching is anisotropic because of the directional bombardment, and also highly reactive because of the chemical reaction. The typical form is the RE, reactive ion etching. So how come the ion bombardment will enhance the chemical etching, will enhance the chemical etch? There are a few possibilities. First, the ion bombardment will help surface adsorption. It can also help etching reaction because of the physical damaging weakening the chemical bond of the material to be etched. So here we have ion bombardment, but those areas they are damaged or weakened, then the etching will proceed. The third is the byproduct removal. So in the case of when we use like a CHF3 gas, there will be fluorocarbon polymer. So this is the film. We have the fluorocarbon polymer film formed on the top and also formed on the bottom. Fluorocarbon polymer. But the fluorocarbon polymer on the bottom will be bombarded away. This way there will be etching. But there will be no etching laterally because of the fluorocarbon polymer. But the fluorocarbon polymer at the bottom is removed by the ion, removed by the ion bombardment. So when we have fluorocarbon, for example, when we have this gas, it will form. So this is the fluorocarbon. So the RE is similar to the PCVD. So when we have this gas, there is chemical etching. There is also the polymerization process. So actually, the RE and the PCVD, they are pretty similar tools, except normally for the PCVD, it's heated to up to 400 degrees, but for the RE, it's normally less than 100 degrees. So here's the first example of the ion enhanced etching. So here we take an example of the xenon difluoride. We have talked about xenon difluoride earlier this lecture. But this is a gas phase etch, no plasma. There is no plasma. As you can see, in this situation, I think this may be a low xenon difluoride pressure, low pressure. So the etching is very slow. This pure chemical etching is very slow. But this ion bombardment. The pure physical etching is also very slow. So when we have this argon bombardment plus the chemical etching, the etching rate is much higher. So this is because of the damage weakening of the silicon lattice by the ion bombardment. So this makes the etching by the xenon difluoride easier. But this way we can have the vertical profile. So this is one example of the chemically assisted ion beam etching. So we will see in the later slide. We have the chemically assisted. So we have this one chemically assisted ion beam etching. We will talk about this later slide. So now let's look at how to get an isotopic profile. So here we have the neutral species. This is the also called a free radical. They come here. They come in by the diffusion. So the ions and electrons, they come here. They are very directional because of the self barriers. They come here directional. If there is side wall reaction, then there will be isotopic H components. It will become isotopic. So we need to prevent the side wall from etching. We need to prevent side wall etching. We can build up a polymer, a passivation layer. It's also called an inhibitor. Passivation layer that will protect the side wall. Then there will be the competition between the passivation and etching reaction. For the horizontal surface, like this surface here, for the horizontal surface, so the etching rate tend to be temperature independent because we have ion bombardment. So when we have ion energy, then thermal energy will not be important. But on the side wall, the surface temperature can play a very important role because side wall passivation depends on the volatility of the inhibitor that is controlled by the temperature. For example, when we have this very low temperature here, this layer can be silicon oxide fluoride at a very low temperature. At minus 100 degrees, this will become the passivation layer. But at room temperature, this one is very volatile. It's very volatile. So even without side wall passivation, lower temperature still increase isotopy because the chemical attack of side wall is suppressed at the low temperature. So now let's look at the one example of the etching profile. Here we use the CH3 gas or CF4 plus hydrogen gas. They will form a fluorocarbon polymer like Teflon. So they will form this polymer on the wafer surface. So this is this layer here. This layer here is this fluorocarbon polymer. So you can see that when we have high inhibitor, inhibitor deposition rate, so the profile will tend to be tapered like this. So when we have low inhibitor deposition rate, when we have the lower, this may be low, not very lower inhibitor deposition rate, the profile will be more vertical. So it is a combination between the etching and the inhibition. When we have very high, if it is very high inhibitor deposition rate, then it will become a net deposition, no etching. So here is the passivation. If we add argon gas, argon will become argon ion. But then the inhibitor will be removed by the ion bombardment. We can also add oxygen gas. If we add oxygen gas, so the inhibitor on the side wall is also removed. But the inhibitor on the horizontal surface is removed. It acts way faster. But at very low temperatures, like as we said, minus 80 degrees to minus 130 degrees, when we use this gas, SF6 and oxygen gas, it will form on the side wall, it will form silicon oxygen fluoride. But this one, at this low temperature, this one become the inhibitor. It will protect the side wall. But this is the cryo-etcher. So the cryo-etcher is also very popular. So we have a cryo-etcher in campus. So here is the summary of the etching mechanism. But this is very important, so I want to say it again here. So because of the very low density, ion itself does not contribute much to the etching. The free radicals, neutrals, they are important. So even with directional ion bombardment, the overall etching can still be pretty isotopic. For instance, SF6 etching of silicon is very isotopic, even with ion bombardment. So then we have isotopic and with large undercut. So to achieve anisotropy, there are two mechanisms. The one is called energy-driven anisotropy. Here we call the damage at the bottom, then the etching will proceed. The second one is called the inhibitor-driven anisotropy. In this case, so we found the polymer here, fluorocarbon polymer on the side, and also fluorocarbon polymer on the bottom. but fluorocarbon polymer on the bottom is etched away by the ion bombardment remove. So ion bombardment remove the fluorocarbon polymer, so the etching will proceed along the vertical direction. Thank you.